Hi everybody, welcome to this JBUS webinar where we're going to be talking about Echosounders and the applications, how to use them, about the accuracy, and I am pleased to be joined by Christianis Linkovics from who's lead engineer from SBH Engineering, lead engineer for their integrated systems, and he's going to help us with a demonstration of the HydroMagic processing software at the end, and also he's going to deal with some of the aspects around the accuracy of the system. So yeah, I just wanted let's get started, because what we need to do today is go through a heap of stuff, and then also have a Q&A at the end. If you do have any questions, please send them in. And we will answer them as we go through. So yeah, let's move on to the first slide. So some of you might be aware, JBUS been going for around about 2 years now. We are partnered with UgCS or SBH Engineering, as they are, under the brand UgCS Integrated Systems. We are dealing on a daily basis with UgCS and acting as a reseller integrator for their integrated systems into the UK market. We work really closely with many of the OEMs of the sensors, so whether it be Echosounder with Echologger, or with some of the GPR or magnetometry OEM. We work in a kind of, as you can see there, in a kind of like a circular motion between the two parties to make sure that we deliver the best service we can for customers who are wanting to integrate these systems and get the best from them from a commercial perspective. So just a little bit over what we do. So you might be aware we've also been dealing in a lot of other sensors, not just with the technology we're dealing with today, but we've done many projects on methane laser systems using the Falcon, integrated with the UgCS integrated system, also using magnetometry from Sensis, and also with the other, for those that have been on the website recently, would have seen that we are also dealing with other versions of magnetometry as well now. If you haven't looked, go and have a look. GPR, we're also dealing with GPR across all the ranges, so from 1000 megahertz, 500 megahertz, 3, 150, 100, and even 75 megahertz on the new LF GPR, which I'm pleased to say we've got our first system going into a very well-known university in the UK very shortly. Also dealing in sonar systems, and as some of you will also be aware, we're also dealing with Worktwell on the thermal side as well. So lots of different sensors, lots of different integrations. If any of this kind of technology seems like it's something that you could deploy in your business, then please come and have a chat with us, and yeah, we'll help you the best we can. So let's move straight on then. Let's move on to what we're here to talk about mainly today, which is the echo sounding technology used for bathymetry and soft sediment analysis, and we will discuss what those mean a bit later on. But let's look at it as an integrated system. Let's look at the main components. So when we talk about an integrated system, what do we actually mean? So we mean a set of hardware and software working together. In this case, in the top right hand corner, you can see that the brains of the operation, called the Sky Hub, and I'll dip in a little bit more into Sky Hub in a minute, but that's an onboard computer. Essentially, that's talking to the drone. It's controlling the drone, what the drone's going to do in terms of its mission, and it's also where we collect data and download data from, and we'll go into that a little bit later. We also have what's called an ODR, so that's an obstacle detection radar, get it right, and that's used for seeing small branches, for example, which are often missed by the standard DJI cameras, front-mounted cameras, and it gives a little bit of extra protection when you are flying. not just in small ponds, or reservoirs, but also in other areas as well, like magnetometry and GPR. When you're flying pretty low, it's good to have that extra protection where the radar will see something that your sensor on the drone will have, or your standard sensor hasn't seen, and it will stop the drone. It will save the drone. So that's always a good thing to have. Obviously, on the top left there, we've got a compatible drone. In this case, it's an M300. And what you'll find today is I'm pretty much talking about the M300. I know now we've got this new M350, probably another one to come as well. But in terms of the compatibility, I think you'll find very quickly that the A350 is also a compatible machine, and we can use that as well. We've got the sensor, which in our case it could be, and again, we'll talk about this later, it can be single frequency or dual frequency, but you can see the sensor there at the bottom, sorry, in the top left-hand side. Bottom left-hand corner, we have another bit of hardware called the true terrain following radar, or terrain following radar, positioned on the front of the drone right there. That kind of, along with the cables that connect the systems together, that is the hardware set. And on the software set, we have three main pieces of software. We have the ground control software, or what I think most people around the globe know as UgCS Pro, UgCS Expert, UgCS Enterprise. They're just yeah, it's the software that allows the mission to be planned in on your laptop. And then the second bit of software that we use is what's called CPM software, or custom payload monitor software. And this is a software that's looking after the payload itself, and it's providing live data as well coming in, depending on what sensor you've got, and it's allowing us to download some data, or the data, into different formats. So it's multi-use CPM. But in real basic, basically, what we're talking about is a piece of software in UgCS Pro that does the mission planning, and CPM software working seamlessly next door to that on your screen, which will look after the payload. Then the third bit of software that we're using is called UgCS for DJI, and it's a bit of software that goes onto your controller, and it allows you to see the mission, and allows you to get a lot of the telemetry. It's very, it's a kind of advanced version of some of the DJI software you'd probably be used to. Very useful indeed. So that is what we're calling an integrated system. So hopefully that has given you some good visuals of what we're talking about. So let's look at the actual kit itself. So if you were to come to JBUS and you were wanting an echo sounding sensor solution, what would you get? So you would get two cases. In the first case, you will get a black pillar case, and in there you'll have your Sky Hub, your true terrain following radar. Next door to that, you can see at the bottom is our obstacle detection radar. We'll have an OSD gate cable, a heavy payload connection attachment for the actual Echosounder itself, and a few other little bits and pieces to allow the easy connection. Moving on to case 2, you can see there that the standard supply includes the Echosounder and the reinforced cable. That's the cable with the connection that will plug into the Sky Hub, and with some clever clever attachment. It's very secure. And then on the far right is the actual Echosounder itself. This particular Echosounder is a dual frequency Echosounder, but there's very little difference between them, looking at them, between the dual and the single. The only difference actually is the weight. All the Echosounders that we're going to talk about today, well, I'll say all of them, the 2 that we're going to talk about today, they're made by the same manufacturer, Echologger. So that's hopefully gives you an idea of the kind of what to expect when you buy a kit from JBUS. So what does it look like when it's on the system? Well, you can see the heavy payload attachment at the bottom there, and you can see that it's hooked, has the Echosounder hooked on. You can see the Sky Hub, and there are maybe a couple of cables connecting the Sky Hub to the drone, Yeah, we've got a true terrain following radar as well. So that's kind of what it would look like when the Echosounder is connected to the bottom of the drone, and you can clearly see that the heavy payload attachment there at the bottom, which is a really good feature because it makes it very secure. So Skyhub and TTF, true terrain following core. Whenever I talk to people, I always call this the core system, because once you've got the core system, which is Skyhub, true terrain following, a radar, you can essentially bolt any sensor you want to it, and that's the great thing about it. Once you've got the core, the Skyhub 3, TTF, and the UgCS Pro software, and the other bits of software that I told you about, you can then just attach, by changing a few things in Skyhub, you can then attach one day an Echosounder, next day a methane, next day a GPR. So that makes it really flexible and a very cost-effective solution for drone survey companies. So what is Skyhub 3? So what's it for? So Skyhub 3 is what we connect the Echosounder into, or the sensors into, and it's responsible for looking after the flight modes. So it's taking telemetry from the drone, and it's then telling the drone also how it should fly. So if we want to fly a true terrain following radar, which is hugging the terrain, then it will tell the drone to do that. If we have what's called, and we're going to talk about this a little bit later, another mode, which is called grasshopper, which is used quite a lot used for bathymetry, then the drone can be told to do that. And Skyhub 3 is also collecting the data, as I mentioned earlier. And then the clever part is it's fusing that telemetry from your drone with the payload data, so that we can then download data which is meaningful, where whether it be NEAM or SegWi or CSV or whatever's required to do the job. And then there's the other feature of the Skyhub 3 is that it's got, there's lots of ways to integrate with it. So you've got power outputs from it, you've got different connection ports to connect different sensors into. So we've got a connection for all of the sensors, and obviously that will change. And also what you will see on the front of the Skyhub there is variable voltage now. That's a recent upgrade, a very welcomed upgrade, and that means that we can easily change the output voltage to various sensors depending on what the application and of course what the sensor is. So why do we use TTF radar? So why use a radar in the first place? What's wrong with just using the drone's barometric altitude? Well, this basically put, and the chart illustrates it there. A lot of you would have seen this already, this kind of chart, but you can't trust barometric pressure at low levels, at low altitudes. It doesn't reduce risk at all, and it increases risk. So using a true terrain following radar, where you've actually got if you like, a much better feed or data for what the height above ground is the way forward. It's the best way of doing it, because you don't get that variability as you do with barometric altitude. Also, as I said, using a radar, you can also use other flight algorithms. So you can use grasshopper mode, and grasshopper, as you can see in the bottom right hand corner, I think it kind of illustrates it, but essentially you're taking the drone to a certain spot, you're dipping the drone down, and if you can imagine, if it was bathymetry, you'd be dipping the Echosounder into the water, you're coming up, you're going to the next spot, you're dipping down, you're coming up, you're going to the next spot, and so on and so forth. Now, the beauty of that is, of course, is that you can go to specific spots in a sort of freshwater area or a water feature, to the places where perhaps you haven't got any weed, or perhaps there isn't very much depth, and you don't really want to go into those areas. So you can choose those areas that you want to get readings from, for safety of the aircraft, but also to get better accuracy of the data. for example, in sediment ponds, you will have areas where the sediment is actually just literally just underneath the water level, or even just above it. And obviously, you don't want to be dropping a bathymetry on that, or indeed pulling it over a stretch where that is present, because it would have to come over the sediment to come back into the water, and that would probably just damage everything. So grasshopper is very useful in those regards, so that you can actually just come up and go to a spot, dip down and come back up and go to the next spot. And you can plan that in quite easily using the UgCS Pro, which makes it really simple. So yeah, so what is really important to note is that this is an integrated system. So to use the echo sounding system sensors and this integrated system, you do need to have what's called UgCS software on your machine. And UgCS Pro, Expert, and Enterprise. Enterprise being the it's kind of what it says. It's the enterprise version, and it allows you to have video feed, multiple drones, multiple pilots. For most applications, you maybe won't need, and most businesses, you won't need that. You probably have 1 or 2 people tops that are using this. So you'd probably just be okay with a single UgCS Pro, Perpetual, or Expert license. For those that don't know, Expert, it has everything that UgCS Pro does, but it has the LiDAR tool set. So if you're flying LiDAR missions, then Expert is probably something that you want to look at. But for 90% of the time, when you're just wanting to fly Echosounder missions, UgCS Pro is good enough. You don't need all these other tool sets. So you fly UgCS Pro, but the thing to remember is you do need this software to use this sensor and this integrated system. So that's that's one thing that you do need to remember. In terms of compatibility of the integrated system itself, then I've just talked about M350 coming out, DJI M350. That's going to be compatible soon without a question. The M300 is compatible, and you can see other non-DJI as well. So Pixhawk or Gcopter, for example, are other examples where non-DJI environments. Okay, so moving on from that, just a little bit about to show you what we mean by having CPM and UgCS Pro on the same screen. You can see here that we've got UgCS Pro on the left-hand side, and on the left-hand side you can see we've got if you were to have this on your screen, you would see UgCS Pro on your right-hand side. You can see some telemetry. You can see the where the drone is going over this lake as it is, and the right-hand side, but actually the top right is where is in the planning of that actual flight, and you can see that you've got some tool sets which a lot of you would be familiar with on the left-hand side, where you can plan in your pass width, and height and all kinds of other not height, speed and other kinds of things. So it's that kind of thing should be very familiar to you. Going back to the CPM, you can see how it can nicely fit onto your screen. You can fly both the CPM and UgCS Pro on the same screen. And when I was saying about how you can switch between sensors depending on what you're doing, then it's literally the drop-down boxes that you can see here where it says not selected. You can take one sensor away and you can put another one in, and it will then, it's with a few other little bits set up. You go and fly that mission with that sensor. It's really easy to do. So yeah, that's what it would look like when you're flying. So let's have a quick look at the Echosounder models. And like I said before, we're looking at just two main models, a single frequency model and a dual frequency model. So let's look at these in turn. So the single frequency is actually 450 kilohertz. It's quite a high frequency rating, and this frequency rating can be used in shallow ponds, and I'll get into this a bit later, that there is actually what's called a dead zone. So you need to be aware of that. But for this particular sensor, 30 centimeters is effectively the echosounder itself in the water, give or take. It can be used with very shallow ponds. There is no sort of dead area where you were on the dual frequency, as I'll talk about later. There is a bit of a dead area, and so it gives you need a deeper area for you to actually start collecting data. But with the ECT 400, it's only 30 centimeters, so fairly shallow ponds, not a problem. You know, ponds, lakes, rivers, streams, as long as the turbidity isn't off the charts, you're fine. As I said, it connects directly into SkyHub, so we are taking the data from the Echosounder and fusing it with telemetry from the drone. And then there are some, as Christianis will go into a bit later, there is some simple mathematics that takes place to get us to where we need to be to give good data. Also with ECT 400, it has a tilt sensor, and that can be essentially, you can set it up so that you can say if the tilt is the tilt of the Echosounder is beyond a certain number, then you think that's not good enough data to be taken in to be used. And like I said, when you have higher turbidity, then that becomes quite important, because you can basically take erroneous data out and say, well, actually that's not relevant, it's not going to be that great. And like I was saying, that'll be talked about a bit later. It is a very light Echosounder in all regards, much lighter than the dual frequency at only 1.3 kilograms. Yeah, that gives you a good flight time. We'll go into a little bit later. It's using we use HydroMagic software as standard. It is a standard supply with this Echosounder. So part of our package is that you get training on HydroMagic, how to use it, and get the best from it. You know, understand the tool sets that are within it. So it's not just about that, you know, providing you with the solution in terms of the equipment supply. It's also about giving you a complete solution, being able to go out there and use it commercially. We'll go into a little bit later on why you use one another. But so our second Echosounder that we have is what's called a DO52. This is the dual frequency system at dual frequency 50 kilohertz and 200 kilohertz. I said before about there's a sort of like a dead area where you need to account for that when you do your data. For example, if you are wanting to go into a shallow area and you've got only half a meter, then you are not going to be able to collect any data, because we need at least 1.3 meters, effectively 1.3 meters for the system to actually record. So you know, it needs to be aware that yeah, you just need to be aware that you've got a dead area below it, and you need a minimum amount of depth. Again, it's just like the ECT 400. It's connecting into SkyHub, same as what I talked about before, fused, and you can download it to different formats, and we'll look at that again in a bit. And yeah, tilt sensor, kit weight, a lot heavier than the single frequency. So you know, again, you're not going to get as good flight time. I'll cover that in a little bit later. And just like the ECT 400, you get the HydroMagic software as well. On the right hand side here, here's a really good example of where you could use this dual frequency. This is for sediment indication. So where you've got a buildup of sediment. I mean, for example, it could be within some kind of river channel, maybe it's a port channel or a side channel. And you are looking to see how much sediment is built up, then the 200 kilohertz, the higher kilohertz rating will give you what would be considered sort of like bathymetry, and your 50 kilohertz would be going through the softer sediments, and giving you some kind of a profile of hard sediment below it. So that would be giving you that kind of depth of sediment buildup over X period. Yeah, and that's how that dual frequency comes together. So the rule is, as long as the sediments are organic, then the system should work fine. Yeah. So using the echosounder systems, you need to bear in mind the main one actually is the velocity of the sound wave through the water. That depends on quality. So in a lot of cases, it's worth investing in a sensor, a sound velocity sensor, so that you can really understand when you're processing the data. We can work that into the calculations. There are other sensors as well. Like I said, you can look for turbidity, salinity, flow speed, and you know, there are others as well. But the sensor that I would, put as something you should think about if you're going to be using echo sounding a lot in different water environments, then sound velocity sensor would be a very good investment. And again, we can provide that as well. So yeah, no, it's all good. So next few slides are looking at why would you use UAV to deploy an echo sounder, and sort of when. So in essence, we're looking at the reasons and what applications. So yeah, but this is the look at those. So a lot of these it's worth just going through. So as I said before, so small and or shallow area or water features, you know, where you wouldn't necessarily want to get a boat out, you know, be very expensive, time consuming. It's much quicker to get a drone out. You know, you can have it up in the air in less than 15 minutes. The back of someone's car, basically, you know, essentially. Hard to reach locations, so where you've got new points of entry, can't actually get to the area. Steep bank, for instance, is a prime example of that. Very easy to get a drone out, get it down, and get the data. We talked also earlier about the grasshopper algorithm, which the radar, one of the benefits of using the tree terrain following radar, or the radar. Great for if you've got seaweed, debris, other mechanical pollution, and like I said, sediment buildup, where you just don't want to be dragging, I say dragging, but pulling the echo sounder through the water. The grasshopper is really good for that, because again, you're able to just choose where you want to do your readings. So fourth, drinking water reservoirs. So in areas where you're not allowed perhaps to have a boat, and then a drone is a really good example where you don't need to have a boat. You can just go out and get go and take the readings. Also, it's really fast setup and easy deployment. So yeah, like I was saying before, if you compare it to other boat deployment, it's much faster. It can be much faster and much easier. So having that in your toolbox can be a very cost-effective approach. And also, you can have very accurate repeatability. So with a boat, sometimes certainly certain boats, larger on the lots of not massive, but I don't know, 6, 7, 8 foot. They move around a lot, and maybe you have you're trying to get readings. It can affect the data. So this is a way of getting very accurate data. As you're probably aware, a lot of you are aware, drones are very stable in the air. With RTK, you're able to control the drone within centimeters on a good day. So you get very accurate readings. And also using the mission control software from UgCS Pro, using this GPS RTK, you're able to repeat the same survey over and over again, like with really good precision. And that can be giving you seasonal variations and lots of other variations as well, of course. But so accurate repeatability, really key. Reason why you would deploy a UAV. And of course, as we said before, as we all know, people who fly drones, they're really maneuverable. So you get extra maneuverability, being able to move the drone to places that you may not, in a very quick way, and able to, in tight spaces, move things, move the echosounder around, dip in, dip out, go to another place, and so on. So there's some really good reasons why you would deploy a UAV. So applications, I've kind of touched on them a little bit earlier. So the first one is, well, the one that I've kind of mentioned already with the dual frequency. But saying that, you can just say that it is for dual frequency, but you can also use a single frequency in this application as well. You just do several readings over a period of time. But yeah, and then you get the sediment buildup. But certainly dual frequency water channel depth mapping, very useful. You can certainly, with a standard ECT 400 for 450, you can see waterway scour identification. So where you have got water is scouring away, you're able to see that quite easily. So that's a very good application of it. As I said before, soft sediment depth indication. So if you've got ponds, for instance, sediment, settling ponds, sediment ponds, then you're able to see how much has built up, and also possibly in water treatment as well. There's a number of applications in water treatment where you have a buildup of organic material, and you need to know how, what the depth of that is and whether it needs cleaning out and so on. So the so a dual frequency echosounder would be really good for that. And then the last one, second one from last, support of primary surveys. So very common if you're flying a mag survey, for example, over in the swash zone, and you need to, or not even the swash zone, it might even be just half a meter of water, but you want to know exactly or for high precision what depth of water that is. Then you can use an echosounder for doing that, and you can then use that in your reporting when you're using a primary sensor like a mag to do some, for example, UxO or other survey. And the last one here is providing data for digital twins. One of the download data types is CSV, and we can take that data directly for use in a digital twin. So if you're using LiDAR above the water level, you can use an echosounder below the water level, and you can get a complete digital twin above and below the water level. So that's where the echosounder could actually, it is already proving its worth by providing that kind of data. So accuracy. So it's an important aspect to talk about, and we'll work our way there. The first thing to say, just to reiterate, and I put this in my chart because I kind of fell foul of this a year ago when I was speccing an ECT 400. Forgot about the depth, about the dead zone, let's say, what they call. It's really important that you remember that if you are dealing in shallow water, that you don't go for something like an ECT 5052, which needs about 1.3, or I say 100 centimeters, 1.3, I think it is actually 1.3 meters. Oh no, 100 from the bottom of the sensor. Sorry, so that's about right. Yeah. So that you don't look for a sensor that has a dead zone, which means you can't get any data. So yeah, just be mindful of that. That if you're in majority of cases, if you're just looking for straight bathymetry, then the ECT 400 is a really good system, and yeah, it will give you that capability in shallow water. So just remember about the dead zone. It's quite important. So for those that are familiar, the nominal accuracy of both of these systems, both the ECT 400S and DO52S, is as per on the screen, 0.2% of the depth, with resolution at less than 1 millimeter. What does that actually mean? You would expect to have a difference of around 10 centimeters or less between what you would expect to get in boat bathymetry. So still fairly accurate. And my understanding is that SPH are working on using other ways to get a better accuracy for the collected data. So we just wait and see about that. But as it stands right now, within 10 centimeters, which in a lot of applications that's still really good. From talking to people and from what I've spoken about. So the other important aspects to remember are that we recommend that you don't fly an Echosounder in wind speeds that are more than 5 meters a second, and you will and for optimum collection of data, flying at 0.7 meters a second. Again, we can discuss that a bit later. If you've got any questions, then please, don't hesitate to send that through. Okay. Yeah, just at the top there, we can see the differences in the flight the flight times. 30 minutes for the ECT 400, and less time for the heavier dual frequency system. So there is a trade-off with having a dual frequency over having a single frequency. Yeah, and it's just something that you need to bear in mind when you're going to fly your mission. You just think about your batteries and the time it's going to take you. So resolution, just something on resolution, just to bear in mind, with a higher frequency Echosounder like the ECT 400S, you have got a narrower beam width. Because you've got that narrower beam width over the ECT DO52, you will get generally speaking, you'll get a more accurate reading of the bathymetry. So if you're doing straight bathymetry, because of that narrower beam width, it does give you a slightly more sort of more representative data, let's say, of the bathymetry. As your beam width gets, as you go down in Echosounder frequency, you find that your beam width becomes wider, and you therefore get it's less representative. So the takeaway from this is, if you're looking for straight bathymetry and you to get the best results, you need to be looking at an ECT 400 with a narrower beam width. That's the takeaway from this. So hopefully that makes sense to everybody. Okay, so this is the part where I'm going to hand you over to Christianis, who's going to give you a little bit of an insight into the next couple of slides. So yeah, Christianis, you want to take over?
Yep. Hello. Do you hear me well?
Yep.
Yep. Okay. So as we are dragging a sensor attached on a rope, and this is not a fixed system, we have some challenges in accuracy. Okay, we want to put this right here so that you know what to expect. So SkyHub will recalculate your depth based on the sensor angle. You will get the correct depth measurement. Excuse me, I will just ask my guys to quiet down. Okay, sorry for that. So, and we have two components in this accuracy. We have the vertical accuracy and the horizontal accuracy. The most important factor in vertical accuracy will be what kind of GPS you have. If you have the basic GPS, like plus minus 1-2 meters, this is not going to be good enough. We need to consider always flying with RTK GPS, where our GPS altitude accuracy comes up to like 1 centimeter or 2 centimeters. And the vertical accuracy of the underwater features will, as Jonathan said, depend on the beam width, the Echosounder accuracy, and GPS accuracy. So this is all the same as for a boat, because we are recalculating the angle. So vertical accuracy will be the same as on a boat. Maybe there can be a slight difference because all the systems are calibrated differently, and we cannot tell if the boat is right or the drone. Okay. So, but knowing the speed of sound in the specific liquid, therefore, is the greatest contributor to vertical accuracy if utilizing RTK GPS. So, as Jonathan already told you, for speed of sound in the liquid in question, you can use a sound velocity profiler. In simpler cases, or if you just want to verify, you can just attach some metal ball or something else at a known distance from the Echosounder, just submerge it and get your own improvised sound velocity sensor. This will, of course, give you the sound velocity only at the top part of the water. So if you have a really strong thermocline or something like that, a sound velocity sensor will still be the better option. Okay, so horizontal positioning accuracy is the biggest problem because we are dragging the sensor's angle increases, and with the increase in depth, we will get more and more of a coordinate shift. So there are a few ways to work around this. The first one is to go slower, and at the recommended speeds of 0.6, 0.7 meters per second for shallow bodies of water. We are already at the maximum of International Hydrographic Organization exclusive order survey specifications. But for deeper surveys, our accuracy falls because, well, we are not, the drone is not in the point that is being surveyed. So this is something that you should keep in mind, and you should always, always, always talk to your customer about what the specific requirements are. Maybe they want a general overview of an area, and then they want to build in some areas, some like a bridge or something like that, and there they want higher accuracy. There, a grasshopper mode, or even just a manual flying with a drone, which is also possible, will be the better option, especially if there are currents involved, because the current will also try to take the sensor away. So what we didn't talk about previously is that, well, you can plan missions with Echosounder, plan a route, and fly fully automated pre-planned route, or you can also use manual flying, which is especially convenient if you are working in surf zones, or if you need to work against current and just find the sensor angles that work for you. So you would just fly around manually and get some data that way. Okay, Jonathan, can we move to the next slide? Okay, so here are the tips about improving accuracy. I already talked about that on the previous slide, but yes, you can use grasshopper mode. You can go slower in standing water, or just break the drone, just go a little slower at some points. You can also match the speed and direction of current, because the current will take the sensor away, and the way around that is to move at the speed of the current. You can also introduce coordinate shift in post-processing. If you know that you have a current against the sensor that will displace the sensor relative to the drone by the same amount all the time, then you can apply that in post-processing in HydroMagic. And we are also looking at other options to deal with this, such as using drone's bottom cameras to determine where the sensor is actually located so that we can recalculate coordinates. But this will work only for very, very specific drones, like the mentioned DJI 300. Most other drones either use incompatible sensors, various systems, or just don't have the bottom cameras at all. Okay.
Great. So just to recap then, before we get on to the HydroMagic software and also a quick sort of five-minute demo. Yeah.
Yep.
So yeah, go on, Chris, if you want to continue.
Yeah, this is something that we always talk when talking about the drone bathymetric sensors, is that obviously if you have a really good boat and it is suitable for the conditions, and you have the time and the funding to get it out to location, then by all means use a boat. And in those cases, a drone can be a useful supplemental tool for your surveys in the shallower areas where you cannot get with that boat. But if you are primarily a drone service provider, this gives you a lot of flexibility in adding, as Jonathan said, to your digital twins. It is much easier to stitch data with LiDAR and drone echosounders than with the ones that's carried on boats. Also, if you are just looking for doing a comprehensive survey, you don't have a boat, you don't have a drone, you will quickly see that getting a drone with a LiDAR and an echosounder allows you to do everything over water, underwater, much cheaper than with a boat. Okay, I think we can. The next step now is going into processing, right, Jonathan?
Correct. So I was just going to talk about just the three, just to reiterate the three data processing types, just how we get the data for processing.
Mm-hmm.
So there are, like we've mentioned, there are three types: CSV, again that digital twin that we talked about earlier, NMEA, which is primarily used for bathymetry because of its frequency, and also we have full segue data, which is used by not just HydroMagic but also other software like HiPack and some of these really expensive software packages. So there is three ways of getting the data out and then being able to use it into HydroMagic software. So just a quick view here of what you would see within HydroMagic to give you sort of like a kind of a visual. We use HydroMagic software simply because it's not high end. It's still got very good tool sets. So it's not complicated to use, ease of use, and it will deliver in 99% of what you need to do. It's got a ton of useful features such as tilt and roll and GNSS correction. You can even do volume calculations within the software, so where you've got one reading versus another, and the software can provide you with that volumetric calculation. You can import geotiffs into it, so just like other software, you can actually see the site as it is right now. And there's also data cleanup feature. If you've got, for example, seaweed that you can see that is erroneous and really shouldn't be there, and it's obvious what that is, you can go very easily and take that away, knowing that you have got a much better visual on the bathymetry. So last thing that I want to say before I hand you over to a quick demo by Christianis on HydroMagic is that as part of the supply, we give full training on HydroMagic. So that's something that you get very familiar with, and it's part of our standard supply. So yeah, I'll now hand you over to Christianis for a demo of the software. So yeah, we've got 10 minutes. I hope that's enough. If we can get Q&A at the end, that would be great. But let's just see how we get on.
Okay. Okay, I will share my screen. Can you enable my screen sharing?
Yep.
Okay. Okay, so HydroMagic. Okay, so in HydroMagic, we would just create a new project. So let's click on new project, enter a name for it, test again. We choose where to save it and what map projection to use. I think for this, we will use any zone one. Usually we just fill in project description and Soraya as well, but this is not required. Next thing that we do is we import the data. We will import the data from NMEA 0183SC log files. There is a lot of formats that you can use, including the SegWit that's also produced by Skyhub. Let's see. Okay, let's select these. So we just choose the NMEA files for this one. And that's it. And then we choose the NMEA sentence to use for single frequency echosounders, or when working with water depths. The preferred is the depth sentence that gives us the depth of the water relative to the surface. But if we want to work with underwater terrain, and if we have RTK, then the more useful is, or if you use dual frequency, then the more useful is SDXDR, which has both low frequency and high frequency. So we will use that for this dual echosounder data here. We do not input any sounder offset because that is already done by Skyhub. Next and finish. So we have imported our raw data files. You can see them on the screen. And next thing that we can do is we can add a map. So we can add a map, either download a map from the web, from Google Maps or somewhere else, or we can import it if we have it. Let's see if I have a map for this location. Okay. Okay, here we see that we are actually over water, and we are using just the same drone photogrammetry. We went there, we used the drone for photogrammetry, and then we used the drone for bathymetry. So we get everything here. We could also just download the map as well. So the next thing to do is to convert this raw data into soundings. And this is where we can apply any sort of corrections, filtering, things like that. So again, we just click through what kind of coordinates do we use, either depth or the elevations from RTK receiver, and whether we have some sound velocity corrections, something like that. Then we can filter the data. We can filter the depth data to only return the values that are actually expected to be there, because as any sensor, the Echosounder will give also some spikes that you have to clean up yourself afterwards. So this is an easy way to get out of those spikes. We can also filter by angle. If we have not set the filtering by angle on Skyhub, we can also here filter by angle to assure that we have quality results. Usually we would have this under 15% or maybe even 10 in case we need to be extra precise. Okay, so we can apply that. Then we can look at the echograms and see what sort of spikes or something else we might have. We can use already functions, smoothing, some median filters on this, or we can just see, well, these spikes are obviously fish or some seaweed, and we just select them and delete them. So this way we can go through all the files. So the red one is high frequency, the green one is low frequency. We can switch to low frequency, then to high frequency, see if maybe there is anything that we need to delete, and we can go like this through all our files just to get a more accurate data, because at a point here, this can be a reflection from anything in the water, and if the water is not clean or it has fish or seaweed or something else, we can get point errors like this. Of course, we can also just do a filter, like for example, a median filter, and just get rid of them just like that. This usually just makes the data smoother. If, again, we have to talk to the customer what sort of quality of data they expect, because especially if you have a lot of files, you might want to just process them quicker, and then maybe some filtering is okay. For the International Hydrographic Organization standards, like even for the exclusive surveys, the minimum feature that is needed is 1 meter square. So if it's a real big cube in the water, then you actually have to know that it is there. But if not, you don't. Again, this depends on what the customer wants and how much time you have for the processing. But anyway, this is just a simple point and click and do your things. Next, we can use edit position data and maybe delete some leading lines to and from the location if we want to make the survey data more perfect, or if we need to use it later on in some presentation or somewhere we might not need this. So we can filter that out as well. And then there are a wealth of additional tools that we can use. We can use offsets. So if you have, for example, a very good idea about that there is a clear border in the water where the depth changes, that would be one of the ways to remove any sort of GPS shift in post-processing. If you know that there is such a border in the water, for example, there is a pipe going through the reservoir or something, then you can use these position offsets or things like that to just line up that pipe on all the data, and that way reduce the horizontal coordinate shift. Okay, so this would be if you have a current shift in a specific shift in like that is happening all the time. And if you have a latency shift, then you can use this latency to adjust some milliseconds or something just to line up a pipe or a fixed some change in depth that you can use as a kind of a fixed feature to align your data to. But usually this is not required, especially if the depth is less than 10 meters, then you are well within all kinds of standards, even the highest ones. Okay, so we won't use that here, and let's click OK. Next, we have to call this sounding something, and that is it. We have converted our data into soundings. Now we can color them if we want. Let's see if we can make them prettier. Let's add some color. Okay, let's use automatic color. So these, when working with XDR, these are not actual depths, these are elevations. So elevation of the border of this lake is around like 81 meters. Okay. Now we have some color here. For the next step, we will introduce a boundary. So we will draw where we didn't make any observations just to get the shape of the reservoir. So now I can do it quick and dirty, but again, you can go as precise as you like.
1 minute
And
left.
let's set the elevation at 81 meters there. And let's use this in matrix generation. And let's quickly generate at least a high frequency matrix for this. So high frequency, let's set the spacing to 5 meters. And okay, let's create a matrix. So the matrix for high frequency looks something like this. We can also do isolines. When we have this data, we can use volume calculations. So here we have volume calculations. If we create a matrix for low and high frequency, we can get a difference of those. We know how much we can dredge out of this, things like that. But these are kind of the basics that you can get here. Also, when you have this matrix, you can export it. So you can export where we can export this matrix. So we export matrix data. We can export it for use together with LiDAR data, or just for HiPAC, or just XYZ point cloud, things like that. Okay.
Good.
This was a quick intro.
Yeah, I mean, one thing that just comes out of that demonstration is how easy it is to do this kind of analysis. Once they have the required training on this package, it really does make things very much easier. It's an easy package to use. So no, thanks very much for that. Okay. I don't see any questions, so I think we must have just covered everything that we needed to. For those that have come on the webinar, thank you very much for attending. If you do have any questions at all, please just send them in. We'll try and answer them the best we can. And yeah, I look forward to seeing you at the next webinar. But thanks very much, Christianis. That was brilliant, as always. And thanks everybody for being on the call. And all take care. Thank you. Bye-bye.
Okay, thank you all.